As you can see here on my shared screen, we're not just joining the 2 meetups today for a special. We also going to talk about 2 new exciting deep learning AI courses that just came out, I think about 2 weeks ago now. And we do have instructors from both courses. Rob has created the AI4Good course, Deep Learning AI. Rob will give us a sneak peek there and show us some highlights. And then Chris and myself, together with a couple of others, Shelby and Mike from AWS, we created the Generative AI with Large Language Models course that came out about in the same week. So we're super excited. Thanks so much, Rob, for joining us today. And we're going to do today's special, a quick, short sneak peek into both courses and going to share the links. So if you haven't started looking into those courses, if you're interested, feel free to do so. And with that, any other words of introduction from you, Chris? Otherwise, I think we'll hand it over to Rob. You're caught off guard there. Okay.
Happy to muted. Happy to take it from here. So, yeah, like Antje said, I just completed a specialization with DeepLearning.AI on AI4Good. So we're covering 3 specific areas: public health, climate change, and disaster response. And I can jump into that now.
I'll stop my share and hand it over.
Oh, my screen sharing is paused. I think somebody needs to unpause me.
How do we do that?
There's a pause. You should have a pause button on your side.
Resume.
Or just, can you, resume.
Yeah, I'm pressing that and it's saying it's pause.
Or do a stop.
Resume isn't working.
Stop and reshare, maybe.
Yeah, just do a complete reshare.
Okay, let's try that again. How's that look?
Much better.
Yep.
All right. So like I said, new specialization, AI4Good, available from DeepLearning.AI that you can watch on Coursera. And in addition to myself, we put the spotlight on a number of people working on really interesting applications of AI to improve human or environmental conditions around the world. So I encourage you to take the course and get inspired by the kind of work that these people are doing. So first of all, what is AI4Good? It's not a great saying, which I think, like a lot of people on this call will know, that some of the best good you can do is ensuring that larger companies have AI that is more fair. And I feel that some of the time that I've worked at large companies has been more impactful for the world than when I've worked, in actual refugee camps for the UN. But here we're talking about very specific applications of AI. So this is when the goal of AI is to prevent, mitigate, or resolve problems that affect human life or the environment. And AI is only one part of any potential solution. So with most of the times I've used AI in especially disaster response scenarios, it's played a fairly small part in a much larger ecosystem where we're bringing in stakeholder needs, community knowledge, and often some very simple explanations. Okay, and we'll be talking about 3 areas, like I mentioned: climate change, public health, and disaster management. So these are all areas that I've worked in the past, in addition to being a disaster responder. So for about 20 years, I've worked as a disaster responder, in addition to working as a machine learning professional. So before I moved to the US about 20 years ago, I was working in Liberia for the UN, installing solar power systems at schools and clinics supporting refugee camps. I worked back in the region again in Sierra Leone, where I'd previously lived as well, during the Ebola outbreak. I worked in Haiti following the earthquake there in 2010. I've worked in global epidemic tracking, including helping WHO in the response to COVID-19. And I ran, my startup at the time ran aerial imagery analysis for damage assessments following Hurricane Sandy in New York and around. And so having worked in disaster response for a long time, and kind of in parallel working in machine learning, I brought the two of those together when I moved to the US in 2007 and decided to complete a PhD at that time. So I completed my PhD under Chris Manning at Stanford University, and I looked at how we could apply natural language processing to 3 different scenarios: the earthquake in Haiti, like I mentioned, that I responded to, a health clinic in Malawi, who are having trouble dealing with lots of communications, and floods in Pakistan that I'd helped respond to in 2010. So since that time, I've done a lot of work combining machine learning and disaster response. And on the industry side, so like I said, I've worked in startups. I was CTO of the largest data labeling company. I worked at AWS, where I was the product manager to launch the first NLP services there, comprehend and translate. And right now I'm at Apple, where I have R&D, on-device machine learning, and anti-fraud teams rolling up to me, which has a lot of interesting problems for us to work on there. So back into this course, this builds on both my experience predominantly as an engineer, but also on occasion as a product manager, and thinking about the entire product life cycle and how you engage in the stakeholders. Can you work out whether AI really can have an impact, and if so, how do you ensure that you're not, despite good intentions, bringing harm? So I think hopefully most people in this course will know that most of our ideas in AI fail. Like, we have some really smart ideas, and then they just don't really pan out, and that's true of a lot of humanitarian work, disaster response, and public health work. And there's no magic when you combine the two. It's really, really hard to create successful AI products, and it's really, really hard to successfully have an impact in humanitarian situations. And so when we bring them together, we have to be really careful at every step of the way that we're not accidentally introducing harms. The context of the course, we talk about it using a framework of the UN Sustainable Development Goals. I think people who work in this area would agree that these goals aren't perfect, but they are a useful way of dividing up the kinds of ways that we can have an impact on the world, and at least provide a common framework for discussing them, even if there's some obvious gaps in what's here. A general principle for humanitarian work is do no harm. And so what this means is that everyone impacted by a project is left improved or unchanged. And this is really important for the reasons I said, in that most projects won't work. And so if you're doing harm to anybody on the way to trying to achieve a greater good, chances are you're just going to do that harm, and the greater good won't come out. And so this is often different to what you'll see, especially in an academic setting, where you're comparing your AI in an offline evaluation to a previous model, and you're just looking for the net benefit. You're not trying to evaluate whether anyone is harmed despite the net benefit. And so that's not something that we aim to do in disaster response scenarios. So I think a really good example is the vaccines for COVID-19. So we didn't skip any steps in getting the vaccines approved. We accelerated things within existing guidelines, but there was obviously a point where we were pretty certain that the vaccines didn't have big side effects, and it would have been a net benefit to roll it out. But it wasn't until we could get to the point where we are today, where it's not even clear there's any deaths from vaccines themselves. It's only when we got to that point that we actually rolled out the vaccine. And this applies to a lot of what we do. We will not do an intervention if we think it can cause harm to people who would otherwise not be harmed. Okay, so in this course, we have 5 labs over the course of the different topics. These are all in Jupyter notebooks. Because we're hoping that we can have people from the disaster response community who do everything in spreadsheets today. You don't need any prior coding knowledge. You can step through these notebooks without jumping into the code. But obviously, if you're interested in the programming side of things, which is probably most people on this call, you can go in and play around with these labs and try different models or hyperparameters. So the first one is pollution detection in Bogota. So Bogota has about a dozen high-quality air pollution detectors, which are the round dust that you can see on this screen. And this lab consists of 2 parts. When the detectors go down, predicting what those values would be, based on both the neighboring stations plus the temporal trend in between those gaps. And then the other is predicting a more precise level of pollution between the sensors. So you can see in this graph here, which is what they do today, they basically treat these sensors as cells and assume that the pollution within that cell is the same as at the tower. And obviously we can probably come up with a better, more gradient prediction for what the exact pollution is at a given point. And then if we look at the lab itself, this is like a good display of what it looks like over time. And with all of the courses, we do some exploratory data analysis to try and understand what we think is a good and is not necessarily a good problem for AI to solve. So you can see in this example here, PM2.5 are particles of 2.5 microns or smaller. These are ones that can cross the blood barrier very easily in your lungs. And so a lot of the time when people talk about pollution, actually specifically mean these very small particles. And what's interesting here is that, which is good for citizens of Bogota, there's not that many readings where the values are really high. But what you probably can intuit from that is that you're not going to have very good predictions about high levels of pollution because you simply don't have much historical training data in that regard. So this can start to give us an idea of the nature of the data and where we think AI might be able to help and might not be able to help. Then you plug that over time, and with other courses as well, we establish sensible baselines. Often an interpretable baseline, which is close enough to state of the art, is better. It's easy to interpret, it's easy to support in production. And so we're not necessarily reaching for state-of-the-art models every time that we deploy. So I like to think of this as an equivalent to Toyota Land Cruisers. So if you've ever worked in international aid, you'll know that half cars seem to be Toyota Land Cruisers. And that's because they're very reliable. There's going to be spare parts and people know how to repair them wherever they're being used. And no doubt you could invent a state-of-the-art car in like a research mode that would be better for international aid. But then supporting that in the field is going to raise a lot of question marks. And so I think knowing how reliable something is, which has been tested for millions and millions of miles before it goes into the field, is often more important for a car. And I think that analogy applies to machine learning a lot of the time here too. It's also just good science to establish a good naive baseline to begin with as well. Okay, the second lab is biodiversity monitoring. And I will acknowledge here that there's all kinds of biodiversity. It's likely that microbes and fungi are as important as charismatic megafauna. But for a lot of reasons, we know a lot more about large animals. And the kind of AI that we've spent more time on, which are things like object detection, is more reliable than what we might use to try and identify bacterial levels, for example. So with that caveat, the second lab is motion capture cameras in South Africa and trying to count the number of animals going in front of them so that we can track changes over time. And this data comes from a very large collaboration of national parks across sub-Saharan Africa, who are all trying to track biodiversity in different areas. The third lab is damage detection after Hurricane Harvey. So like I said, this is something that I've done before as well, but actually not for Harvey, I did for Hurricane Sandy. And it's image detection on satellite images, trying to predict whether a given satellite photograph shows damage or no damage. And this is an interesting problem. And again, we do exploratory data analysis. We look at the most significant features in terms of which pixels in a given image. And basically, we conclude that we made a water detector, which is not bad as a first pass, I guess, if you're specifically looking at flooding in an area that you know historically that doesn't have water. But that's not exactly the same thing as predicting damage. So I think it's a good example of predicting a kind of like a secondary feature to the actual thing you're looking for. The fourth lab we look at is predicting climate change. So looking at what's mostly rising temperatures around the world, but there's spots getting cooler, especially where there's ice melt in the oceans, and trying to predict what the future will look like with different scenarios of carbon reduction. The fifth lab is exploratory data analysis following the 2010 earthquake in Haiti. So following that earthquake, I found and managed about 2,000 people in the Haitian diaspora who could translate between Haitian Creole and English. So while 100,000 people were killed immediately and millions were left without access to safe drinking water or food, most of the cell phone towers remained active. But the majority of people in Haiti only speak Haitian Creole, and the majority of the international community only had English as a common language. And so by finding these people in the Haitian diaspora, they were able to do real-time translation of emergency text messages sent from Haiti so that we could stream those translated and now geolocated messages back to the international responders in the nation. We did this for about 80,000 messages and I think about 20,000 are in this data set. We removed any that might have had any kind of PLI whatsoever, following guidelines that the Haitian community came up for us about the sensitivity and privacy in the data. And so this is exploratory data analysis. And this is looking at, okay, what can we do with like topic modeling to find out what we missed? Every disaster is unique. You'll see that this data set, if you take the course, has a lot of standard categories. I think about 30 different categories of types of disaster, like requests for food, water, information, etc. But there are going to be specific things that I know that we missed as disaster responders. And so yeah, even today, more than 10 years later, you can do analysis and find pockets of information that were really important that we just didn't see, or types of requests that aren't categorized. And that's valuable for us as disaster responders so that we can better plan for future ones. Okay, and that is it for that course. So I hope if you're interested in thinking about the different kinds of problems that you might work on using AI, that you'll take this course.
That's amazing, Rob. Thanks so much. And I want to call out, I called it a course, but it's actually a specialization, right? So you've built 3 courses. So yeah, what's kind of the expected time for people to go through the course?
You know what? I'm not sure. I signed up to do 1 course, and the deep learning people tricked me into turning it into 3. Certainly some people got through it in the first weekend since we released it. So hopefully they slept. So I guess I guess it's on the order of like 20 hours total, something like that.
Nice.
It depends on how fast you want to speed up the video of me speaking as well. Right.
So you can binge watch the thing, but
yeah.
No, that's amazing content there. I've just peeked into a little bit more of the details. It's an AI and public health course, AI and climate change, and AI and disaster management.
That's right.
So yeah, if folks are interested and they haven't signed up yet, let me repost the link here. Definitely this, and you definitely win with the animals in the course.
Yeah, it's my wife who taught me that. She's a biologist. Like biologists hate everyone who focuses on charismatic megafauna, and they're always telling people that there's all kinds of animals that probably matter more. But
Yeah.
it's at least we can teach that bias, even if we kind of address it in the course.
So maybe yeah, and I know I'm joking around a little bit here, but it's a serious topic, the disaster relief and preparedness. So what do you think is the biggest challenge in the disaster response space? Is it the availability of like data sets to work with more AI?
Yeah, I mean, there's not that many data sets, and disasters are very unique from one to the next. I think, and I say this in the course as well, some of the best things we can do are ensuring that things we take for granted in English, like search engines and available information on Wikipedia, reliable news services with misinformation filtered out, that all of that is available in as many languages as possible. If you speak a less widely spoken language, you're much more likely to be the victim of a man-made or natural disaster. And so a lot of the work that I've done is enabling communication. So when there's a disaster somewhere, like people come to me and say, okay, what languages are spoken here, and how do we get information to them?
Right.
So if there's already good machine translation systems, good information available online, just better speech recognition in a language, so that people can just find information for themselves, then that's some of the most important things that people can do.
Yeah, and I see here a question if the data is usually open source. I think so, right? The community is usually sharing.
It really depends. A lot of the time it's sensitive, and so we typically don't share it. In the case of Hurricane Sandy, we thought the images, which were taken from a plane flying over, could identify too much. So we shared that data with another independent organization who could evaluate how well we did with the image assessments, and then we deleted it all. In the case of the data from Haiti, we work with that community. We deleted everything related to a child alone, because that's, we think, a sensitive subject that you shouldn't predict. And then everything that contained even a first name, on the off chance that someone could even just identify themselves and understand this was a traumatic experience for them. So yeah, in that case, the data source is open, but a lot of the time it's really sensitive. And well, I said AI for good is kind of a complicated term. AI for bad isn't. There are a lot of people that prey on in particular, disaster impacted communities. So in COVID-19, it was a clearinghouse for oppressive regimes to get rid of political dissidents. So you'll see that many oppressive regimes defined misinformation to include any criticism of the government, and all started labs for misinformation identification. And some of those organizations are publishing that information online. So which Twitter user, without telling that Twitter user, is saying something that disagrees with their government. So we have to be really sensitive about the kind of information that we can put on.
Yeah,
but
that makes sense.
We worked extensively with these data sets, and so you'll see for the ones with the charismatic megafauna, we removed any that contained vehicles or people who were inadvertently in shot, and we considered this carefully in the Hurricane Harvey use case too.
Right, that makes sense. Yeah, I think I was thinking more along the lines like the climate data sets and stuff like that.
Yeah, climate data is definitely open. Yeah. And there are some organizations you could trust. NASA has great
NASA has great stuff. Yeah,
information for things like that. Yeah.
Maybe one more question here. What about the prerequisites for the course? So, I mean, your experience is very extensive in the space of disaster response, right? So for people taking the course, working through the data prep, data analysis there, like how much domain-specific knowledge is required?
None. So you, like I said, like I'm hoping disaster responders can come from just using spreadsheets, which is what, and most of public health is just on spreadsheets. So these notebooks are the next best steps. They're importing the kind of spreadsheets they already work with, and then using AI to help make predictions and fill missing values and things like that. We try to give as much context as possible for each of the labs. That you don't need to be a domain expert. But having said that, we emphasize in all the labs, if you're doing this in an actual deployment situation, you would work with experts and stakeholders who are involved.
Right. And yeah, there's a lot of if you want to I think we're going to transition slowly over, but if you want to keep answering a few questions here, people asking about the community knowledge and stakeholders. How easy, challenging is it to deploy and operate initiatives after a disaster, given lack of communication coordination between public authorities? So I think there's a lot of like complex angles, and you called it out, like every disaster is a little bit different and unique. I think regions have their unique challenges probably as well, right?
They do, yeah. I'm happy to continue to answer questions on the chat. I'll jump over there and answer people's questions so we can move on. I guess, yeah, the last thing I'll remind people of is that there really isn't that much money that goes into disaster response. So WHO and CDC both have less funding than Stanford Hospital, and a lot of people look to WHO to help guide us through COVID-19. And they had smart people, but their biggest focus was still maternal health during that period, not COVID-19. So I think, these are very under-resourced organizations. So I think there's a great potential for AI to scale things. But like you said, it's very complicated based on different locales in the world.
Right. We appreciate all the work you're presenting today, but obviously all the work that went into the course here, so folks can learn a little bit more about how AI can be applied in scenarios like this. Any questions from you, Chris or Rob?
Oh, yeah, Robert, thanks so much. Yes, good to see you. I have so many questions, but yeah, we'll take it offline.
Yeah, we can catch up later. I'm super excited to see your course. So I'll let you take the floor.
Perfect.
Cool.
And people are asking about vector databases. That's a good transition. So Rob can answer that in the chat. Thanks so much, Rob. And let me bring up the next screen share here in the second course we're going to talk about. Let me just, yeah, I have the screen up. So let me share. And let me make sure I keep an eye here on the chat in the meantime. And Chris will stay on the camera here too, because he co-developed the course with me and two other of our colleagues at AWS. All right, so again, I posted the link here for Rob's course, AI4Good on DeepLearning.AI. If you want to hop in there and learn more about how AI is applied to disaster response use cases, super exciting. And we're gonna do, I know it's a it's a different transition, but we're gonna talk a little bit more about generative AI with large language models. This course, and Chris can put the link here in the chat as well to this course, we've put together, we launched the same week with Rob's course, and we're super excited. Everyone out there is excited about generative AI. And we've put together a course that teaches a little bit more the fundamentals. So it's not really what you would expect from AWS instructors usually. So we don't talk much about AWS. We really focus on kind of the academic fundamentals, working with large language models, working in the Gen AI space, which is super exciting and hopefully helps you to prepare if you haven't had a chance to do much in that space, if you want to learn a little bit more about the academic foundation, why foundation models and LLMs are so powerful. And if you already started taking the course, thanks so much. We just, as a fun fact, we just crossed the 51,000 learner enrollments after now a little bit over 2 weeks that the course is live. So thanks so much if you're one of them. We hope you enjoy the course. If you haven't taken it, feel free to also enroll. But we're going to give you some good reasons today. So let me jump over to some of the highlights from the course so you know what to expect here. So we're starting, so we have a one course, which is slotted across 3 weeks of content. So I'll walk you a little bit through the highlights from each week here that we're covering. And again, you can also, of course, binge watch the whole thing over a weekend. This is just like a suggested pace of learning. So we're going to start a little bit with the basics here. So if you're new to the space, to get everyone on the same page, obviously we're going to talk about LLMs. So we're going to touch on a little bit the capabilities, the reasons for its success. We're going to talk about how the abilities have been growing with the scale of those models. So you can see here the size of the bubbles. And throughout the course, we're going to focus on the FLAN-T5 model to implement a lot of the use cases and the demos. And Chris will show a little bit sneak peek into the labs as well. With the course, we do have 3 hands-on lab exercises where you can get a little bit more hands-on and play around with the different concepts that I'm going to show you here. Again, we're going to do a little bit of introduction. So if you're brand new to this, don't worry. How did we end up talking about prompts? We had NLP and language models for a long time, but just now with the rise of the foundation models and LLMs, we're going to start about prompt and completion. So we're going to make sure the terminology, we're all on the same page. And let me just go through the animations here. And again, we're going to talk about what happened between BERT and these days when we have models like Bloom or GPT-4, and it's really kind of the significance of the scale there to capture the language understanding. In the first lesson, we're also gonna do a little recap and dive into the transformer architecture that powers the LLMs. So in case you kind of skipped the topic in the past, we're going to give you a chance to learn a little bit more about the transformer architecture. I think most of us have heard about this attention is all you need paper. We've seen this diagram on the right, but in the course, we're really going to dive a little bit into the details here, why the transformer architecture is still around, why it's powering all those really great models. And it's really coming down to 3 points here. The transformer architecture is really efficient in scaling. It can process in parallel, and the attention mechanism, of course, that helps to capture the meaning in the input sentences. So we're going to talk about that in much more detail in the course. We're going to walk you through the individual components here and how they relate to each other. So this is really helping you to have a good foundation. Then we're also going to talk about prompting and prompt engineering. So I think this is what most of us start experiencing LLMs with. We start optimizing here. There's a context window and in context learning, right? So we're going to start looking into things like a 0-shot, 1-shot, few-shot prompting, what that means. So you're providing examples to the LLM to kind of nudge it in creating the outputs that you like. And during prompt engineering, the important thing is you're not touching the actual model. So you're not training the model, you're not changing any weights. It's really kind of influencing the model outputs at inference time by either changing the wording in the prompts or by providing these examples here and kind of teaching the model at inference what you want to see in the output there. All right, and again, everything comes down to the power of the scale, given models this ability to now be able to perform that in context learning. Also, in the first week, we're going to talk about the specific configuration parameters for inference. So you might have seen this if you're playing around with models. You have those playground experiences where there's suddenly a new set of parameters for you to configure, right? It's not the hyperparameters that you're used to during model training. This is really the inference parameters and configuration, like the maximum number of new tokens to generate in the response. We do have parameters like top K, top P, and temperature that give you control over the creativity of the outputs, right? Like how deterministic is the output versus how creative and random is the output the model is creating. And there's a little bit of art and science to them. And we explain this in more detail in the course as well. So here's just one example, the temperature. Cooler temperature means I'm a little bit more deterministic in the next token the LLM is picking. So in my outputs from the model. And as I increase the temperature, we're going to go a little bit more creative. And you can see it here on the probability distributions that are flipped around here on the side. In the cooler temperature, it's really going to go for the most probable next token. And if I have the high temperature, there's a little bit more freedom and I'll have different completions here. So one that's important to understand as you're playing around with those language models. All right, and then we're wrapping up the first lesson here with an introduction to your project lifecycle. So I saw Rob also had kind of the project scope in his course. We have a similar outline here for the Gen AI project lifecycle. So obviously you start defining the use case, you then look for a model to choose. Either you choose a pre-trained one, an existing one, and just apply prompt engineering to get to your results, or you might want to pre-train your own. In very few cases, you really need to do that. And that's really when you have like a very specific domain language. Let's say you're working in the finance industry, you're working in the medical industry, where like the terms are just so much different, the vocabulary from what those models might have been originally trained on, which is the general, maybe internet, Wikipedia, books, corpuses, etc. We're also diving into a little bit more how to adapt and align the model. So this is talking about fine-tuning techniques and also aligning with human feedback, the famous RLHF, reinforcement learning from human feedback. How to evaluate the models is part of that as well. And then in the third week here, we're talking about how to integrate LLMs into your applications. That means, how do I optimize and deploy the model for inference, techniques to reduce model sizes, etc. And then also really exciting, the last part here, how can we augment model capabilities and really implement them into kind of the broader system to power applications, which means giving maybe the model access to additional knowledge sources, data stores outside to retrieve more documents, more information, and also kind of how to orchestrate the language model inside of a bigger task. And I'm gonna show a little bit more what that means in a bit. After the lesson and week one, we do have a lab, and I'm going to walk a little bit through the highlights here, and then Chris will give you a sneak peek into those labs as well. All right, we're going to talk about scaling laws. So in the rare case that you have to pre-train your model, there is considerations, again, as I said, whether you really have to do that. But we're going to talk about this as well briefly in this course, and how pre-training looks like, right? So you're going to have a vast amount of data. In the case of LLMs, it's text data, unstructured, and then the model basically builds up the vocabulary here. And obviously, this is a very compute intense task. This is where the model trains for weeks, for months, to really capture all of that understanding. And sometimes a fun fact is that you collect all of the data, and only 1 to 3% of the original tokens actually make it to the data set. And this is just because you really have to curate the data and make sure, you're not introducing any harmful content that just, human language is out there in the raw input text sometimes. All right, we talk about the different architectures, and I'm going to really go fairly quickly over this. The course talks about this in much more detail, but we're going to talk about what's the difference between autoencoding models that are based on the encoder architecture of the transformers, what are autoregressive models that are based on the decoder only side, and then also the third one, sequence to sequence models that are using both parts, the encoder and the decoder parts. And each of them serves a specific purpose and are well used to these days. Encoder-only models, maybe BERT, are really good in creating embeddings, are really good in the reinforcement learning process later on, for example, to be used as reward models. And then the more usual candidate for the generative text generation models are the autoregressive decoder-based models. But there's also really a good use case for sequence to sequence, for example, if you're doing language translations, etc., which is generating text input to text input. Again, we're talking about this trend of like models getting bigger and bigger. And there's actually a really good discussion around scaling laws, if that's to be continued. We're going to talk about this famous error that you might have seen out of memory. So we're going to talk about the computational challenges that you might see working with the models just because of the size. So we're going to teach a little bit more about how much GPU RAM is needed to store your model and also to train your model. And here's just an example. if you want to store 1 billion parameters, this translates to 4 GB GPU RAM needed at a 32-bit full precision. And we're explaining that part also in much more detail. What you can do here is reduce the precision to reduce the amount of GPU RAM needed, so you can fit larger models into maybe potentially one instance, but usually definitely you have to scale. So as you're exploring this, for example, you will learn that there's much more data that needs to be stored than just the parameters. So you have optimizer states, etc. And this basically ends up in 20x more memory needed. So to train the model, this would easily now translate to 80 GB of GPU RAM needed. So again, we're going to talk about this. We're going to also talk about how you can tackle this with, for example, quantization. We're talking about all of the different types here, from full precision, FP32, to half precision, floating point 16, to a new format called bfloat 16 as well. And then also sometimes you would even quantize down, reduce to an integer value. And we're also talking about when does it make sense to distribute. Again, sometimes the model is just too big for a single GPU, and sometimes the model might fit, but you want to speed up the training by training with data in parallel. So you have the model on each, for example, but you're splitting the data across. And we have two techniques here. One is the DDP, the distributed data parallel, and the other one is called fully sharded. So one is splitting the data, the other one is also sharding parts of the model across GPUs. All right, scaling laws, just quick here. The research community actually observed a couple of trends that some of the models might have benefited from shorter training time, but on much more data. So you end up potentially with models that don't go into the trillion of parameters anymore, but maybe stick into kind of the tens of billions of parameters, and are much easier to really kind of work with on a day by day. And there's a couple of scaling choices you can have. You can usually, you fix the compute budgets, the amount of GPUs you have, and then you can make choices of how many parameters the model will have and how much data it's trained on. And there's a famous paper called the Chinchilla paper that we discuss in the course as well that explains the benefits there. And again, this will end up in scaling laws here that give you kind of a ratio between the model size in numbers of parameters and, given a fixed compute budget, how much training data it should be trained on. All right, and again, week 1 has a lab on prompt engineering and in context learning. I think I need to go a little bit more distinct here in the interest of time. But then we talk about fine tuning. So this is jumping into the second week of the course where we talk, okay, let's say you can use a pre-trained model, you had pre-trained your model, whatever, but you want to customize now with your custom data. And this is usually what you'll do. You'll select one of the foundation models that are available that fits your use case best, and then you can make a choice to fine tune it with your custom data. And a lot of those pre-trained models are already fine-tuned with instruction prompts, but we're going to walk here a little bit through what that means and how to evaluate. So in this case, you're providing your specific data that is label data. It's a supervised training step. So you have the prompts, you have the completions, and there's a couple of different ways to do it. There's fine-tuning a model on a single task. Let's say you want to just train the model to summarize on your specific data. And you're also going to introduce the instruction, in this case, summarize the following text. And the one important thing here to note is that you need far less data for the fine-tuning step. So for this task, for a single task fine-tuning, usually only 500 to 1,000 examples are needed. And then you can also do multitask instruction fine-tuning. So if you want to keep the ability for the model to reason through different tasks and be really good at different tasks, you would have different examples in that fine-tuning step. So fine-tune it through a mix of tasks. And then obviously you need more examples here. We're going to talk about the evaluation. So if you heard about Rouge and Bleu, we're going to touch on that and the benefits. And we're also going to go into the different benchmarks, Glue, Superglue, Helm, Big Bench, MLU. So a lot of things to understand here, how you can evaluate the performance of the models. One highlight here in the week 2 is after we talked about the foundations, instruction fine-tuning, there is this very popular new concept called parameter efficient fine-tuning, short PEFT. And the idea behind PEFT, there's a couple of different techniques, but the most popular being here in the middle called LoRa is how can I optimize this fine-tuning so that I'm not retraining and changing all of the parameters in my model and only minimizing that to really kind of a minimum amount. And this could be sometimes as much as only 1.5% of the parameters. And there's different techniques to achieve this. The most popular one that we see is called LoRa, low rank adaptation of LLMs. And I know this is a very busy slide here, but basically what you're doing, you're reducing the rank of some of the weight matrices in your transformer architecture to a lower rank. And this reduces and you freeze the rest of the model. And this gives you like a really small amount of parameters to train, and you're reaching almost the same accuracy of your model, which is exciting. And there's a lab, which Chris will show here in a bit on how to do that actually. So you're going to apply LoRa in a hands-on lab as well. Then I'm coming now to the 3rd week of our course. We're going to talk in much more detail about reinforcement learning from human feedback. This is a technique, and I'll just quick forward here, a technique to help align the models. It has been discussed extensively, I think, over the last couple of months, since we've seen how models can perform, how well they can be aligned to humans, especially like if you want to align the model to be more helpful, to be more honest, so not to start hallucinating, and to also change the tone, so respond in a harmless way. And here's just a couple of examples what this can look like if the models behave badly. So what you can do is you apply reinforcement learning to change and align how the model responses look like. And we're going to walk through all of the steps in the course. Here's just a quick primer. You're going to collect feedback data from humans. So you're going to have a sample prompt and a couple of completions. And then what the humans will do is they're going to rank the responses. Here, for example, for the helpfulness, which of the different responses, completions are the most preferred ones. And this is going to end up as your preference data set. And the goal is to actually train a model that's called the reward model in capturing those human preferences. So you're going to prepare the data, you're going to prepare that for training data. That means you're splitting those completions that we had from completion pairs into pairs here. And from the human feedback, you know which one was the preferred one. And you're going to use that data then to train the reward model that is used in reinforcement learning. And just to quickly jump here. So in reinforcement learning, you have your LLM, you want to kind of align the model output to be more helpful, less harmless, etc. And the way we do this is we're feeding data. We're using a reinforcement learning algorithm called PPO. And as the LLM produces prompt completion pairs, we're sending it to the reward model. And the reward model has now this understanding from being trained on human preference data, assigns a score. This is the reward in reinforcement learning. And the more aligned the response, so the more towards what we want to have the model produce as output, the higher is the score. If the model suddenly gives us a response, a completion that we don't want, the reward would be really low. So we would discourage bad behavior, encourage the good behavior in terms of which tokens and how completions should look like. And then reinforcement learning will basically train and fine tune the model here until we reach a threshold. And we're going to talk about this in much detail. There's a lot more to talk about here, like we can also make sure it's not going too crazy into the reward hacking and just coming out with ridiculous completions because it's the highest reward. And there's something called a KL divergence that gets added to the reinforcement learning term, which again, we'll talk in much more detail. We also talk about, just briefly here, constitutional AI, which is another idea to kind of align models. And this one here is sometimes called reinforcement learning from AI feedback, where you're able to actually scale that human feedback part by having a model that can self-critique its responses and create this preference data set. So super exciting. Again, I have to call out here, most of this is still active research areas. So every day we see like new ideas, new papers coming out. So this is a snapshot, but super exciting to see what's being discussed. And then the third lab here that's be part of the course is you're actually getting hands-on to perform RLHF and generate more positive. In our case, we have creating summaries as our task. And I'm going to stop here. We do have another part that's talking about optimizing LLMs with advanced prompting techniques, how you can, for example, do chain of thought reasoning and then integrate the LLMs into applications. For the sake of time, I'll hand it over to Chris here, who will give you kind of a sneak peek into those 3 labs as well. And Chris, if your lab environment is up.
Yeah.
I'll do a stop share here on my side.
Okay, taking over the screen. Can you hear me okay? See me okay?
Yes.
Okay. So yeah, I think I'll focus on the PEFT and RLHF because I think those are probably 2 notebooks that the audience likely has not seen. The other notebooks or the other lab, so lab 1 is taking dialogue. So think of it like customer support dialogue and then summarizing it so that you just get the gist out of it. Maybe you're looking for specific complaints. Lab 2, we actually take that data and we fine tune a large language model. In this case, we're using FLAN-T5, which is a really good general purpose model to use for lots and lots of different use cases. And so here's that data set. It's called dialogue sum, so dialogue summarization. You can find it out on here on Hugging Face, for example. Just go to data sets. And you'll see there's training test and then validation here. You can go to the dataset viewer. And here you see, if you drill in, you can see this dialogue here. Most of the names have been anonymized. There's places where it still has some first names and things. And then this is the summary. So this is human curated summarizations of these dialogues. So humans have gone in and labeled, I believe about, what is this, 13, 14, maybe 14,500. So close to 15,000. And there's also topics which we do not use in this lab. All we're doing is just taking a look at this dialogue and then summarizing it. So we're going to use PEFT for this, and PEFT is parameter efficient fine tuning. And so this is a variant of fine tuning. Now, fine tuning is where you have your own data set. For example, I saw lots of questions about this on the chat. Hey, I have my own data set. These language models have been trained on sort of generic data, public data sets, but I need to get my data in there. And there's a couple different ways to do it. One of them is using, LangChain and retrieval augmented generation, which we do cover in the course. The other way is to fine tune, and then this is specifically PEFT fine tuning. And it's pretty straightforward. You give it the name of the model that you want to use. You can actually change this out for different types of models. So someone on the chat asks, how do I keep up with all these models? I don't really know what's the best one. And quite honestly, this is a challenge, and you will always be tempted to use the next latest and greatest model. There's a certain point, where it's not really worth it to keep fine tuning and trying these different models. Just pick one. Like I said, FLAN-T5. It's a relatively old model, but it's actually very, very widely used, and lots of customers that I work with directly are seeing like great success with FLAN-T5. There's different variants, FLAN-T5 XXL, for example, just more parameters, potentially trained on more and more data. But then all we have to do here really is, grab a sample, what we'll call prompt here, and so the instruction that I'm asking this model to do is to summarize the following conversation. Give it the conversation, and then this is the output indicator, which is where should the model start to complete this prompt. So prompt completion, which is like request response. And so here's the baseline human summary, and then here's what my model generated. So this one didn't really do that good of a job. So that's why we're going to do this fine tuning. Okay. And what we do is we construct a prompt data set using this data with, just think of it like a Python template, like a Jinja template that can create a whole bunch of these, summarize the following conversations with the actual conversation, and then the output indicator here, summary colon. And so all of that then feeds in. We just use a small subset of data just for this lab purpose here. You can certainly run it on more data, train for longer. Pardon the scroll here. I just want to get to the good stuff. So, and when you are instructing the model, right, like giving it a whole bunch of instructions during fine tuning, you then have what's called the instruct version of the model. Now now FLAN-T5 actually is already instruct fine-tuned. And what we're doing here is we are further fine-tuning with our data set, okay? And so here, after showing it a whole bunch of these conversations, now the model's getting a little bit more accurate here and is starting to summarize. Now, that's kind of qualitatively, I can look and see how does this compare. Here's the human baseline. This is, the original FLAN-T5, which is instruct fine-tuned, and then our further instruction fine-tuned model. Okay. So let's compare. Oh, and then we do a bunch of qualitative checks here, and so these are all in the labs. And by the way, the labs are paid for by AWS. So all you have to do is just sign up for the course, log in, you will get access to all of these labs and can run all of these yourself. So there is this metric to quantitatively measure these summaries relative to the original dialogue. And that's called Rouge. So I think Antje actually went through Rouge, or just briefly showed it. In the course, we actually go through some of the math behind Rouge. It's a somewhat controversial metric for evaluating these types of things, but it is a good baseline, and it's always good to have baselines, as even Robert said during his talk. So in the improvements of the instruct model, which is actually our instruct model, not the FLAN-T5 or the base FLAN-T5. So by doing this instruction, we actually added about 18% for the Rouge 1 metric, Rouge 2, Rouge L is for the longest common sequence. And so we do see a quantitative improvement. Okay, so that was actually fine-tuning, full fine-tuning. So stepping back a sec, I said that we were only going to cover PEFT. I actually did cover the original, I guess you would call it the inefficient fine-tuning. Now we're going to get into the parameter efficient fine-tuning. And think we're kind of at time here, but let me just zip through and get to, so PEFT, we are only actually training. As Antje mentioned, we are sort of reparameterizing and like representing these larger matrices as lower rank matrices. And in fact, I can configure the rank right here, 32. I could actually go down to rank 4. So, think of rank as the skinny, like skinny dimension on these two, smaller matrices. And let's see, so in this case, I only have to train 1.4%. So this is not 14%, this is not 140%, this is 1.4%. So we see only 3.5 million of these parameters are going to be trained of the original, this is 250 million. Right, 1, 2, 3, 2, yeah. And previously up above, I was training all 250 million. Now, let's zip down and look at the Rouge score. And that's the qualitative. So here we see our PEFT model. Let me just get to the improvement. So PEFT over the baseline is still pretty good, even though we're only training 1.4%. Now, PEFT over the fully fine-trained, which is what I had done way up top, instruct model, we do lose a little bit on the Rouge score, but we had a whole bunch of savings in that we didn't have to use a super large GPU or a cluster of GPUs. I was able to do all of this in a single machine. And the actual model itself that's generated is much, much smaller. It's on the order of 10 megabytes versus 1 gig for the full for the fully fine-tuned model. So that's that. And then real quick, I'm just gonna get right to the good stuff here. So RLHF is where, like Antje mentioned, we're sort of softening these responses from the model. So this is another variant of fine-tuning that is going to use reinforcement learning. We don't have time to show those details. It's all in the course. Yes, Antje actually managed that whole section of the course and goes into a lot of detail. We pulled in a scientist from within Amazon to help us sort of dive into the loss function and some of the complexities there. So a whole lot of detail there. But just know that we were able to lower the toxicity of this model's responses. Now, this model is not very toxic to begin with, so we weren't expecting a huge improvement. But actually, after running for only about I think 3 to 5 minutes, we were able to lower toxicity by about 15%, which is pretty cool. And of course, the longer that you run it, the more and more the model can see like more data and can start to sort of modify the weights within that model. And so all of this, so the start of lab 3 actually uses the output of the lab 2. Yeah, so just ignore these numbers. This is a slightly different version. But so we take the PEFT model that was trained or that was fine-tuned on our data set. We started with that and then applied the reinforcement learning and sort of softened. And if you're wondering about the reward function, you may or may not be wondering what did we use? We use a BERT model, actually by Facebook, and it's the Roberta Hate Speech Dynabench R4 model from Facebook. This model was trained, I believe, out of a Kaggle competition from a few years ago. All you really need for your reward model to say something is toxic or not toxic is just a relatively small BERT model that can do classification, right? Like binary classification. And so, here we see the example here. So I kind of showed you the result, and now I'm just kind of backing up a tiny bit just to show the key parts here, which is the reward function. So passing in, I want to kiss you gives me a not hate, almost 100% not hate. If you start to get a little toxic, then we start to see this shift, and hate is about 97%. And so that's the reward function. So we're running through all of these prompts and then completions, right? So I pass in dialogue, I'm going to get back a summary from the model that I fine-tuned in the previous lab. And then we're going to make small adjustments based on how toxic that result is, that combination of prompt plus completion. And so here we just go through some of the reward stuff. And this is the other key here. There's this library called PPO. So this is the algorithm. Actually, the library is called TRL. I believe it's Transformer Reinforcement Learning. Was created, I believe, by someone who works at Hugging Face, but it's not exactly a Hugging Face project, but it's used, it's super compatible with the Transformers library from Hugging Face. And then PPO Trainer is what we use to make those small little gradient adjustments to the weights of our fine-tuned model from the previous lab. And the rest of it is just sort of boilerplate code. You know, here's where we're pulling out that reward after we do make the prediction here, which is the sentiment pipeline. That's calling the Roberta BERT model and pulling out the reward. And then all of that goes into the gradient backprop, and then out comes a less toxic model, and you're good to go. Yeah, Antje, any questions?
Yeah, we're already over the 3 H's here. I know it's confusing. Helpful on this list.
Helpful. Yeah, did you put it in there? Okay.
Yeah.
The tricky one is harmless, because it's like opposite, right? So you're trying to optimize the 3 H's, therefore you want to optimize harmlessness, not harmfulness. So actually, funny story, it's really easy to flip the order because this particular reward model returns hate in the 0th slot, being 1, or or the like logits for hate is in the 0th index, and not hate is in, or wait, is it the other way around? Let me check. The first slot is not hate, and that's usually where, and that's good, but the 0th slot is usually where the negative index comes from. And so the first time I actually went to use this code, I just kind of zoned out. I was listening to music or something, and I was suddenly optimizing for hate. And it was very, very clear in my results what was happening there. But the end results here, and so the warning there is just like double check that you're using, because you can swap in any other type of reward model. If it's a binary classifier, maybe you're just going to use IMDb sentiment, for like IMDb reviews, which is perfectly fine. And in some cases might actually be better, because this data set is not very toxic to begin with. It's not something that was exposed to the public and, has gone through, right, like lots of like terrible things. It's a pretty clean data set. So even just doing something like positive sentiment or like negative sentiment, and so I can go out and grab right, like any other reward model, and then swap it in, and then I just have to flip what's negative and what's positive, and so that's why I was really clear here and just added this not hate index, which I think I define way up above here, just so I'm using it consistently. But the end result here is, this is the prompt. In TRL PPO land, this is called the query. This is the response before, this is the response after, this is the reward before, and then the reward after. And now, so what happened here is we actually improved the reward. And here, this is the reward for being not hate. And also the reason why this is 1.4 and not something like a percentage is because we are actually using the logits and not the percentages. It's just a convention. You actually could use the percentages, but it's just how I chose to implement this. And so we see for the first maybe 5, 10 here where I actually do, and you could sort of qualitatively compare, this is the original dialogue, and then we see a little bit of softening here. every run gives you slightly different things, but instead of disgruntled, it might slightly change it to not happy or less happy, something like that. So yeah, so this is the harmless H we are trying to optimize for. Yeah, Antje, anything else?
Yeah, I think, one question, how to train a model if the data is not really accurate or confirmed, like operations data, etc. I think that's not specific to RLHF, but I guess a general question.
So operational data, yeah, I think, yeah, I mean, you need some type of ground truth, right, to say what's accurate, what's not accurate, or sort of generally. But yeah, not specifically like a RLHF question, more of just kind of a ML type of question. But yeah, that's generally what you need to do, is just find some sort of ground truth. And that could be human labeling, in which case you should go out and pick up Rob's book. Yeah, there's that. I think I pasted the link here. But yeah, anything else?
I think that's it.
And this is Rob's book. Check it out. And is Rob still on the line?
I'm here. Yeah. Thanks for the shout out. I appreciate it.
Yeah, and you can see my purchase history here.
Where's your rating?
Yeah. Oh, yeah. Funny. You did this during the pandemic as well, too. I remember.
I did. Yeah, I was actually doing this while advising WHO, and a team there was using it as I was writing draft chapters for some of their analysis for WhatsApp messages related to COVID. Yeah. So it was very much inspired by the importance of human expertise, which is certainly true of all the humanitarian work I've done. And I like that it's getting prominence in new kinds of generative AI too.
Mm-hmm. Mm-hmm. Yeah, for sure. And are you working on anything currently? Are you going to do another deep learning course? One of the short courses?
No, I have 2 kids under 4, and I promised my wife I would do no other extracurricular activities in the short term. So maybe in a few more years.
I know. Yeah, I'm a bit burned out too, but Rob, thanks so much. I'm excited to go through your course. Yeah, good to see you again.
Yeah, great to see you both. I really enjoyed your presentation too. Congrats on having so many people signed up. That's awesome.
Thanks so much.
And yes, we'll catch up offline, Rob. I have a lot of questions for you.
All right.
How's that return to work policy going? Yeah, that's always fun.
That's definitely an offline question. Thanks to everyone who asked questions in the chat.
Thanks everyone for joining today. Thanks, Rob.
Bye.
Bye-bye.